Okay, so I was told that when I should give a talk at this time of the day, I should show less equations and much more pictures. So let me start with a couple of pictures. This is actually the first result from my new experiment in Cambridge. So I want to start with the experiment. This is the vacuum chamber that we started to build up. Actually, construction started close to 3 years ago. We have a 3D mod, 2D mods for the export, magnetic transfer, and in the end, everything happens in a glass cell. We started in earnest half a year later when we broke the rubidium cell, and we had started to have rubidium in the system. Then a few months later, we had built up lasers, we had a first mod, and then we had a BEC, again a few months later. And since then, we increased the complexity of the system quite a bit, which actually means that we put a lot of extra optics. The glass cell is here in the middle, and this is obviously some kind of optical lattice potential. And complexity is kind of the key word, because naively, what do you want to do if you want to increase the complexity of your system? If you come with a quantum computation, quantum information background, you just say the first thing you do is you just increase the size of your Hilbert space. A single qubit is trivial, 2 qubits you can give your students as a homework, 5 qubits is already hard work, and 100 qubits nobody can do yet. So just increasing size seems to increase complexity. But of course in condensed matter physics we know that this is not fully true, this is too naive, because at some point we run into a limit, we run into the limit when the system sizes we're now considering are already much, much bigger than all of the intrinsic scales in the system. If you think of scaling functions, if you think of a normalization group, at some point the scaling becomes trivial, where more is just more of the same. If you can describe 1 liter of water, you can also describe 10 liters or 100 liters of water. There's not much new physics coming in. If you want to have a bigger system with more new physics, you really also want to have new structure emerging. You want to have new structure on all length scales. So if you have a certain Hamiltonian that gives you some nice physics on a certain length scale, if you now want to make a system 100, 1,000, 1 billion times bigger, you would also want to introduce new length scales to the physics. And of course, that's a game that we have been playing for quite a while. There are certain ideas what you can do. You can add like an extra interaction. You can add magnetic order. You can have cavities. So you can try to put in one and one more length scale by hand. And then you can ask what would be the limit of that. Can you ever get something that just length scale-wise is as complex as, for instance, wood? Where you start on the scale of atoms and molecules and then macromolecules, then a cell, then structures built out of a few cells, and structures built out of a fiber, and so on. You have new and new length scales, the bigger you get. And this gives you a complexity that I would claim nobody can calculate the DC conductivity of a piece of wood ab initio. Not because it's too systematically complicated, just because it's too much. The complexity in that sense is too high. So how do we do this? How can we get this? Nature does this by self-organization, by fractality, and you all have seen these pictures of logarithmic spirals or the self-fractality, the self-similarity of fans. So what can we do? We can do the same thing, also in mathematics, by going for something, for instance, like the Fibonacci chain. This is a model that you all have seen, but I guess most of you don't know where it comes from. It's a model of 2 replacement rules, where B in the next generation turns into an A, and A turns into AB. You've all seen the consequences of this model, but I guess most people don't know what it's originally thought for. The original idea about this model was to describe the population of rabbits. B is a pair of baby rabbits, A is a pair of adult rabbits. So if you have a pair of baby rabbits, you wait, they become adults. If you have adults, in the next generation they're still there, but they have babies. There's just one simple assumption, they always come in pairs, and they never die. But then you can play this game, start with a pair of babies, have a pair of adults get babies, the babies become adults, now you have to read from right to the left, and the adults get new babies, and so on, and so on. And the length of these strings that you now produce, these are the famous Fibonacci numbers 1, 1, 2, 3, 5, 8, and so on, that you all have seen before. If you now focus instead not on the numbers but on the string is actually rather remarkable. It's long-range ordered, meaning there's no randomness in there. There cannot be randomness because we just constructed out of these simple rules, but it's also non-periodic. It never repeats itself. And that's a structure that we will call quasi-periodic. And it's long-range ordered really in the sense that you know from physics, that you know from condensed matter physics. If you say take an implementation of this as a lattice, take the Fourier transform to get to the structure factor, then you actually get the structure factor that looks like this. It's just a set of well-defined sharp delta peaks, similar to what you would get for an ordinary lattice, but it's a dense set of delta peaks. The structure factor, in fact, is self-similar. If you take one of these regions with big peaks and small peaks, you zoom in that the small peaks become big peaks, you will have the same structure of small peaks emerging again and again and again. This is a self-similar structure going on all the way down. As this structure goes down all the way to very, very small momenta, it means it corresponds to longer and longer and longer length scales. So in a very obvious way, or maybe not so obvious way, these non-periodic structures also really have not only long-range order, they also have novel structure appearing on all length scales. They never become trivial. There's always something new happening here. And now, this is a kind of system that we now want to create with atoms, but we want to go one step further. We don't want to do this in 1D. We want to do something roughly similar in 2 dimensions. There's another way to think about the same systems, that is to start with higher dimensions and come down. Another way how to create the same lattice is to start with a very simple lattice in 2D, just an ordinary square lattice, and then you take a stripe and cut out all of the lattice sides in this stripe and project them down onto this line. And if this stripe is now under an irrational angle, the golden angle in particular, then the structure you get down here is again a structure like the Fibonacci chain that never repeats itself but is long-range ordered. This is a one-dimensional quasicrystal. And this one-dimensional quasicrystal inherits a lot of properties from its two-dimensional parent, which is rather nice, which means it gives us a one-dimensional picture into two-dimensional physics. And in fact, I guess, I don't know whether Ulrich will talk about this tomorrow, but they could show that in photonic quasicrystals, they could create one-dimensional quasicrystals where the edge states are really characterized by first Chern numbers, which is inherited from the two-dimensional parent Hamiltonian. That was an experiment, and it just theoretical work a little bit later. They could also show that you can create 2D structures that inherit topology from a four-dimensional parent Hamiltonian. After the previous talks, of course, I don't have to tell you what this is about. You can go into the direction of 4D quantum Hall physics and so on, and you can think about a lot of nice physics. But there's, again, another way how you can think about this. If you're in 2D, you can also think about what are the rotational symmetries that are possible for a two-dimensional crystal. And it turns out there's just a few ones that are possible. It's 1, 2, 3, 4, and 6-fold rotational symmetries that are allowed. And you can see this by geometry very, very simple. If you say this is a lattice point, this is also a lattice point, so this is a lattice constant, and I assume I have this 4-fold rotational symmetry, then I can build up this structure which nicely closes onto itself, and I get a square lattice. If I say I assume a 6-fold rotational symmetry, I can do the same game. This is a lattice constant, another lattice constant, another lattice constant. This gives me a triangular lattice. If I now try to do the same thing with an 8-fold rotational symmetry on the other hand, I'm in trouble. I still assume that this is a lattice constant, but then I go up 1/8 down here, and I get a point which is closer to the origin than my original lattice constant. So this cannot be the lattice constant. So the lattice constant must be smaller than this thing. But now I can make the same construction again, and I again get a smaller and smaller and smaller length scale. And it turns out, if you turn this argument around, you can also go to longer and longer and longer length scales. So this cannot be a periodic crystal. And this was, of course, well known since 1900. So it was a big surprise in 1982 when people saw, then Cheshman and co-workers saw electron diffraction pictures with a 10-fold rotational symmetry. They would argue that this must be something with long-range order because it's very sharply well-defined peaks. It's not like an amorphous material, but it's 10-fold symmetric, which can't be. There was a long debate that started whether there's quasi-crystals, as these materials became to be known, or whether there's just some things like quasi-scientists, which don't know what they're doing. The debate went on for a long time, but at some point it was settled, and it turns out that these structures have been well known in mathematics all along. Just think of the Penrose tiling. It's a system where you do not have one type of unit cell that you repeat, but you have two types of unit cells. And then you have a set of matching rules which tells you how you're allowed to put them together. And these matching rules, they constrain you so much that there's only one way how you can do it. So the structure that emerges has no randomness, and the structure that emerges is really a self-similar fractal structure with long-range order. And it's a little bit hard to see the self-similarity in this picture, but you can always take a group of, say, these tiles, replace it with a bigger tile. You do this all over the place, and the same structure emerges again, just on a bigger and bigger scale. And in fact, all of this, of course, was worked out. So these are now officially also crystals. Quasi-crystals have been now included in the official definition of what a crystal is. And then the co-workers got the Nobel Prize in Chemistry for this in 2011, so not so long ago. So this is now what we want to build. How can we build this? And here I now start again with the work that was done previously with 4 dimensions. Oh, one more thing I should say maybe, is the structure really complex? How can we quantify complexity? Well, we can do one thing. We can look at this paper by Toby Cubitt, David Perez-Garcia, and Michael Wolf, which is about the undecidability of the spectral gap. This is basically a theoretical work that tells us that if you take a lattice Hamiltonian and you make it bigger, 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 the question of whether this Hamiltonian will stay gapped or whether it will become gapless in the thermodynamic limit is an undecidable hard problem. And they could show this by mapping this question onto basically a universal Turing machine. So the ground state of this Hamiltonian encodes the evolution of a quantum phase estimation algorithm, I don't know what that is, followed by universal Turing machine, which means it's hard. It's like of the hardest problems that we know in computer science. And the interesting part about this is that for the proof, they had to use aperiodic tilings. So this does not work with an ordinary periodic lattice, presumably because at some point you can predict the thermodynamic limit very simple because you enter some kind of scaling regime, but you have to stay with this aperiodic tiling where there's always new structure emerging at longer and longer length scales. So how can we build such a thing? Well, we can start in 4 dimensions and can say, let's build the simplest lattice we know of in 4 dimensions. The 4-dimensional hypercube, the 4D square lattice, as Hannah called it. Just saying we have reciprocal lattice directions along the x, the y, the z, and the 4th direction. And then we say we take this 4-dimensional structure and we now project it, similar to this cut and project method in the beginning, we project it down into the 2-dimensional plane. If we do this with the following simple projection matrix, we actually take the x direction and project it onto x. The y direction stays the y direction, but the original z direction we now project onto the first diagonal here. And this 4th direction, maybe I should also start calling it w, we can put onto the other diagonal. Which now basically means that we have these 4 reciprocal lattice vectors spanning our 2-dimensional space, and it's of course an overconstraint, an overcomplete set because it's a 2-dimensional space with 4 reciprocal lattice vectors in it. But it's actually something that's rather easy to build in the experiment, because the only thing you have to do is you have to superimpose 4 one-dimensional lattices. So it's a 1D lattice with a beam and then a mirror so that you get a retro beam, and you just have to superimpose 4 of them. And actually I want to really advertise this system mostly because of its simplicity. You don't have to do any cross interferences here because you really just have k and minus k from each lattice vector. You don't have to stabilize any fibers. You can just offset them in frequency. They don't have to talk to each other. And if you now don't believe all of my explanation that this must be a quasi-crystal because of this projection matrix and being over-constrained and so on, you can also actually say, well, this gives me obviously an 8-fold symmetric situation in the plane, and 8-fold cannot be periodic because it's crystallographic forbidden, so it's gotta be quasi-periodic. It also cannot be random or amorph because there is no randomness in there. It's just 4 laser beams. There's no way for randomness to enter here. And it's all classical laser beams, so no fluctuations and so on are important. Okay, so I convinced you that we can build this structure. And in fact, you saw a picture of that on the first slide. That is our complex optical lattice arrangement in the 2-dimensional plane. And then we can ask if you have it, how can you show it? What should you do? And here I can explain something that's even easier than what Wolfgang did in the very beginning. I can just say, if I take an optical lattice and you think about this in terms of the photons, the fundamental process is that an atom starts absorbing 1 lattice photon and then does a stimulated emission in the counter-propagating term and thereby changes its momentum by 2h per k. So this is even simpler as the Raman transitions we heard about earlier because we don't have to change the initial state. We don't have to change the internal state. This is a purely scalar problem. Which basically means that, okay, every 2 photon transition changes your momentum by plus minus a reciprocal lattice vector. And you all probably have seen these typical pictures that you get when you do this in 1 dimension. You can say, I start here, and then I can go to this point, and this point, or this point, and this point. And these are the typical pictures that we use to diagnose our optical lattices. And then you can think of them also as the lattice sites in a synthetic dimension. So that now your synthetic dimension is a tight binding model in momentum space. And you can say, okay, basically these Raman transitions are now hopping elements from this area to this area to this area. And this is actually something which is also the basis of Bruce Gatway does in Raman-Champagne, and he has nice models where they can do this with 10, 15 frequencies to really make all of those things resonant. What we can do is we can say, okay, let's do Kapitsa-Dirac diffraction. So just switch on this lattice for a very short time. So to allow each atom to do 1, 2, or 3 of these 2 photon transitions, and then see what are the momentum states we get. If we do this with a 1-dimensional lattice, so only 1 lattice beam present, and of course it's retropath, then we get this 1-dimensional structure of peaks. If we do this with 2 lattice beams, we get a 2-dimensional structure of beam. If we do this with 3 lattice beams, we already see, okay, now we are over-defined in 1 direction, so 1 direction is periodic. The other one turns already quasi-periodic, and if we do it in 4 dimensions, we get these wonderful octagons, which I will now explain in a little bit more detail. So how can we think about this, and how can we know that this must be a fractal? The easiest way is to really follow it through step by step. Let's say I'm an atom and I sit here at 0 momentum. Now let's say I do the first 2 photon scattering. I can go into 1 of 8 momenta along this 8 direction of the octagon. I have these 4 reciprocal lattice vectors, and of course I'm time reversal symmetric, so I also have g and also minus g. So I can go into any one of these 8 states. Let's say I go into this one here, the one to the right. Now I again do the next one. I can again have 8 possibilities. One brings me back to where I started. Another one brings me, for instance, up to here. Again, at this point, I have 8 possibilities. I can go to these 8 states. And you can see 2 of those states are in the direction of where original states was. So here was an original state. Here is now one state in the 3rd order. And they form another small octagon in here. And I just do a little bit of geometry, and I realize that the scaling factor from the big octagon to the small octagon is just the silver mean, 1 plus square root of 2. And of course, this whole construction I can do around every point. So meaning, if I start with this big octagon, I also get like a small octagon around this point. If I start with the octagon around this point, I also get an octagon around this point. So you get the message. This really is self-similar around every point. And with higher and higher orders, my set of peaks that I will observe gets denser, denser, denser. So really it is, I can think of this as a quantum walk on a fractal. I can jump from one momentum to some discrete other momenta, again to some discrete other momenta, and I can follow this around for arbitrarily long time and see to where I get to. So here I do this for 1 microsecond pulse, so I basically just mostly do 1, 2 photon scattering and go to any one of these 8 peaks. If I now take a longer pulse, I can start from these 8 peaks and go to other peaks. For instance, this one is the 3rd order peaks, and then even longer pulses to different other orders. And because these pictures are so nice, here's one blown up. And you can also see there's now 3 octagons in here. They're all scaled by the silver mean, so you can really see this fractal structure. If we would follow this for longer, we would get closer and closer and closer back to the origin. And for the experts, the key feature that enabled us now with this nice data quality, which is quite a bit nicer than last year, is that we are now working with potassium-39 at the 0 crossing of the Feshbach resonance. So this is really to a very good approximation non-interacting atoms. Because if the atoms are interacting and they fly away from each other with different momenta, they can always scatter, and you have all of these overlapping scattering spheres, which form one big amorphous background that you don't want to see. Okay, this is the qualitative picture. Can we also get a bit more quantitative? What is really the physics in here? So what you see here is now just measuring the occupation in the 0th to 7th diffraction order as a function of the pulse duration, and initially for a 2-dimensional lattice configuration, just an ordinary square lattice. What you see is that the initial BEC first gets depleted and the atoms get transferred into the 1st and then the 2nd order peaks. But then they kind of turn around and come back. And you can easily understand this because, of course, the particles still have kinetic energy. So when you think of this momentum space picture as a tight binding lattice, it's a tight binding lattice with an harmonic trap. So they walk up a hill and then get reflected and come back down again, and it's a periodic oscillation. And you can really see how they go from 1st order to 2nd order and back to 0th order to 2nd order to 0th order and so on. It's more or less periodic. If I do the same thing now in 4 dimensions, with a 4-dimensional lattice, I should expect something totally different, because now I can go first sideways in this direction, but then go in another direction, and then come back to a point which is close to the origin, but not the origin. So my kinetic energy is not a big problem anymore, because I have lattice direction in this 4-dimensional space, where there is almost no kinetic energy penalty. And indeed, if I do this, I can now easily see population following it up to 7th order. And if you would, this is all single shot data, if you would average a little bit more, we could go to even higher orders. And you can see that there's some fraction of the atoms that like evolve like a light cone and just expand outwards. So we really can do now a quantum walk in this 4-dimensional lattice space. And if you're not yet convinced, we can also try to analyze this quantitatively by focusing on the first part, the first few microseconds, where you could expect that kinetic energy does not yet have time to act, so it should look like a homogeneous lattice. You can think of this in particular, like in the Fourier limit, where the pulses are so short that you cannot resolve the different kinetic energy states, so it must look like a homogeneous lattice. So what I plot here is the RMS momentum as a function of the lattice pulse duration for 1, 2, 3, and 4-dimensional lattices. You can see the 1D is the slowest one, while the 4D one is the fastest one. And when you think about this, this also makes perfect sense, because what you have is you have a separable potential. You have a hypercubic lattice, so x, y, z, and omega or w are independent direction, and you can just sum over all of them. Which basically means that if I think of what is the total momentum, RMS that I would get is the square root of a term kx squared plus ky squared and so on. So it should scale just like the square root of the dimension that I put in. So let's rescale everything. Let's take this RMS momentum and rescale it with square root of d, and indeed they all nicely fall onto the same first line. So you can really see this is a quantum walk in a homogeneous d-dimensional lattice with 1 to 4 dimensions. At least for the first few microseconds, then at some point kinetic energy comes into play and it becomes more complicated. And I think this is another nice tool on how you can create synthetic dimensions, which is independent of initial states. So we can now maybe do initial states on top of that. So if we take ytterbium and take both the magnetic and the electronic one, we can maybe go up to 60. So 60 quantum Hall, who knows? And I should also say that this one is just limited by the lattice step we had at the moment. If you do a cascading protocol where you have like intense and very short lattice pulses, it should be easy to like extend this up to much, much higher scales. Okay, and just the next step to follow up. Of course, if you now think about this potential in real scale, real space, it's a very complicated potential which is long-range correlated, but it should still have the similar localization physics than what we know from a Bose class in 2 dimensions. So it would be interesting to look for this. We can also ask what happens if I just have a little bit of this quasi-periodic admixture in a strongly correlated model. How does this, for instance, change the nature of the mod transition and so on? And indeed, I can ask, what can I do with quantum Hall schemes? Can I develop some modulation schemes to like do charge pumping in 4 dimensions and other nice things and explore the physics there? So with this, I want to thank my team. This was basically built up by a couple of PhD students. Konrad Fiebern is now close to finishing and will then go to ETH Zurich. Matthias Prossier will finish next year and is an excellent, technically very strong student who is still looking for a position. And Ed Carter and Ju Chun will stay with me for a little while. And I guess in this session I have to show the same slide that everybody does. Also here, postdoc positions are open and applications are very welcome. And with this, thank you for your attention.